This is section 8.2, which is on series and convergence. It's day 3 of the Unit 6 notes. We are going to be evaluating some infinite series, finding if they converge or if they diverge, and then if they do converge, what they converge to. So a very, very basic series here asks us to find the sum of the values starting at 1 and going to infinity of 1 over 3 to the n. So if we just start plugging in 1, 2, 3, and so on, and then adding them up, it would look like this. So we would get 1 over 3 plus 1 over 3 squared plus 1 over 3 to the third plus 1 over 3 to the fourth. I don't know why I put a plus sign there. And so on. We then can use our calculator to approximate what that is. And we get about 0.4938. If we keep going, so the next one would be 1 over 3 to the fifth. 0.4979. 1 over 3 to the sixth. 0.4993. And hopefully you're starting to see that the more of these we add up, it is getting closer and closer and closer to 0.5. Here I'm at 0.4999. I forget how many nines I said, but anyway, there's 3 nines there. And we're getting closer and closer and closer to 1/2, right? So as n continues to get bigger and I continue to add, this eventually is getting to 1/2. So the goal is to be able to tell, first of all, that it's going to get closer and closer to something, and then to find what that is without just typing numbers in. Example 1 here asks us to find the sum as n goes from 1 to infinity of 1 over n plus 1 minus 1 over n plus 2. And again, we're going to do this simply by plugging values in, at least initially. So if I plug in 1, I get 1 over 2 minus 1 over 3. And then the next number I plug in is 2. This is going to give me plus 1 over 3, and then I've got minus 1 over 2 plus 2. And then plug in 3. Plug in 4. Oops, that's a minus sign. And hopefully we can recognize here that minus 1/3 plus 1/3, that's going to cancel. Minus 1/4 plus 1/4 is going to cancel. Minus 1/5 plus 1/5 is going to cancel. Minus 1/6, the next number I plug in is 5, plus 1/6 is going to cancel. Everything's going to cancel except for some of the terms, and in this case only one term does not cancel, 1/2, and the answer again is 1/2. The answer is not always 1/2. This type of function, this type of series, is called a telescoping series. The telescoping series is a series whose partial sums eventually only have a fixed number of terms after canceling. So everything's going to cancel out except for a fixed number of terms, a certain number of terms. Usually ones like this will look like this, where we have one term minus some other term, both in terms of I here. To find what it converges to, you can only do it by plugging in values, seeing things that cancel out, canceling them out, and going from there. So like this one here, if I plug in 1, I get 1 over 1 minus 1 over 3. And now I plug in 2, I get 1/2 minus 1/4. 1 over, now I'm plugging in 3. 1 over 3 minus 1 over 5. And then I'm plugging in 4. 1 over 4 minus 1 over 6. Notice minus 1/3 plus 1/3, minus 1/4 plus 1/4, minus 1/5. The next term is going to have a plus 1/5, minus 1/6 plus 1/6. So I have a finite number of terms, a fixed number of terms that don't cancel. 1 plus 1/2. One and a half, 3/2 is correct. Sometimes these sums are given like this, where they don't necessarily look like they're telescoping, at least not yet. This asks for the sum as n goes from 1 to infinity of 6 over n squared plus 3n. The first thing we're going to do is use partial sums to simplify this. So 6 over n squared plus 3n. We want to use partial sums to rewrite this. So first factor, write it as a over n plus b over n plus 3. Multiply both sides by n times n plus 3. So we get 6 equals, when I distribute, the n's cancel, so I get a times n plus 3, plus here the n plus 3's cancel. This isn't anything new. We've done lots of problems like this. If n equals 0, this goes away. I get 6 equals 3a, so a is 2. And if n is negative 3, this goes away, and I get b is negative 2. So I can rewrite this whole sum as the sum as n goes from 1 to infinity of a over n, 2 over n, plus negative 2 over n plus 3. And now it is a telescoping series, so we can start plugging values in. So we get 2 over 1 minus 2 over 4. Because they're all 2 over, instead of reducing this 2 over 4 to 1/2, I think it's easiest if you just leave it as 2 over 4. Oops. Move this down here so I have a little more room. So we plugged in 1, plug in 2, gives me 2 over 2 minus 2 over 5. So notice my positive ones, my minus one starts at minus 2/4. So that's where I want to start canceling. Plug in 3 is going to be plus 2 over 3 minus 2 over 6. Plug in 4, plus 2 over 4 minus 2 over 7. So now I've got that plus 2 over 4, that one cancels. And the next one's going to have a plus 2 over 5, and then a plus 2 over 6, and then a plus 2 over 7. So we get 2 plus 1 plus 2/3, 3 and 2/3, 11 over 3. So those are telescoping series. The other type, which we just looked at earlier, we said this was equal to 1/2, is a geometric series. A geometric series is simply the sum of a geometric sequence. So the sequence here, when we plugged in the numbers, remember we're 1/3, and then 1/9, and then 1 over 81, nope, 1 over 27, and then 1 over 81. Notice to get from one term to another, it's times 1/3, times 1/3, times 1/3. So this is indeed a geometric sequence because we're multiplying by the same thing over and over again to get from one term to the next. A geometric series, first of all, it converges. It only converges if its R value is in between 0 and 1. If this common ratio, this thing that we're multiplying by over and over again, if that is between 0 and 1, if the absolute value of it is between 0 and 1, then it converges. So it needs to be between -1 and +1. A is always, it's going to be the first term. Notice if n starts at 0, if you plug in 0, you get A times 1. So that's the first term. Don't worry about this starting at 0. I would just remember it's the first term over A, or 1 minus R. R is the common ratio. So if we were doing this problem, I would think about this as the sum as n goes from 1 to infinity of 1/3 to the n. 1 over 3 to the n is the same as 1 to the n, which is 1, divided by 3 to the n. 1/3 all to the n. So it does converge. It converges because the common ratio, the thing we're raising to the n, the thing we're multiplying by over and over and over again, is in between 0 and 1. So it does converge. To find what it converges to, we take the first term, so plug in 1, gives us 1/3, and divide by 1 minus the common ratio, which is the thing we multiply by over and over again, which is also 1/3. So we get 1/3 divided by 2/3. 1/3 times the reciprocal. And notice we get 1/2, which is what we were getting before when we were messing around with the calculator. So it converges if the absolute value of R is between 0 and 1. It diverges if the common ratio is greater than or equal to 1. So example, whatever we're at, doesn't say, asks if each of the following series converge or diverge. If they converge, we are asked to find the sum. So this first one, I have a number to the n. Number to the n identifies it as a geometric series. If it's geometric, what we're doing first is deciding if it converges or diverges, and we do that by checking the common ratio. The common ratio, which is 2/3, the absolute value of 2/3 is less than 1, therefore it converges. To find what it converges to, we plug in 1. Gives me 4 times 2/3, that's the first term, over 1 minus the common ratio. Common ratio is the number you're raising to the exponent. So it converges, and we find that it converges to 8. Part B, 6 times 4 to the n divided by 3 to the n. Doesn't look necessarily quite like this one does, but we can rewrite this so that it's 6 times, I've got 4 to the n over 3 to the n. That's the same thing as 4/3 to the n. Now it looks very similar to this one. My common ratio, which is 4/3, is greater than 1, therefore it diverges. And this last one here, I've got kind of 2 different geometric sums. I've got 1/4 to the n, and I've got plus 1/3 to the n. What we can do is we can find the sum of this one and the sum of this one. If they both converge and I can find each sum, then I can add those 2 sums together. So we're going to do it kind of as 2 different pieces. They do both converge. Notice the common ratio here is 1/4. The common ratio here is 1/3. So if I'm just looking at the 1/4 part, if I plug in 1, my first term is 1/4. The common ratio is also 1/4. So I get this part converges to 1/3. This part over here, the 1 over 3 to the n, I would do 1/3 divided by 1 minus 1/3. We actually did this part earlier. You should get 1/2. So this converges to 1/3, this converges to 1/2. So the sum of the two, 1/2 plus 1/3. The whole thing adds up to 5/6. I'm going to skip example 5. We're going to do a bunch more similar to that later. The last thing we need to talk through here is called the Nth Term Test of Divergence. The Nth Term Test. And it simply says that if the limit as n goes to infinity of a sub n is anything except 0, then the sum diverges. If the limit as n goes to infinity of the sequence is not 0, then the series diverges. Notice it does not have any condition for convergence. If I change this to if the limit as n approaches infinity of a sub n is equal to 0, that does not tell me that the series converges. This is only something that can be used to show that a series diverges. So the last example here, example 5, asks us to prove each of the following series diverge. Part A says the sum as n goes from 1 to infinity of 4 times 3/2 to the n. A couple different ways you could do it. I think the easiest way is to recognize that this is a geometric series. We're starting with 4, and then we're multiplying by 3/2 over and over again. So I would state that this is a geometric series. Where r is greater than 1. 3/2 is greater than 1, it's geometric, therefore it diverges. Part B, it is not geometric, does not appear to be telescoping. The other thing you might want to try to see if it converges or diverges is the nth term test. So if I take the limit as n approaches infinity of this guy here, 3n squared minus 4n plus 1 over 4n squared plus 6, I get 3 over 4. Degrees are the same on the top and the bottom, so we divide the leading coefficients. Which is not 0. Therefore, based on the nth term test of divergence, the series diverges. The reason for that is if I were to list out all the values in this sequence, so we've listed all the values, they eventually are getting closer and closer to 3/4. So they're not exactly 3/4, but they're really close to 3/4. In a series, we're adding them up. So if I'm adding something over and over, I'd be adding about 3/4 every time. So the sum is going to get infinitely large because I keep adding something on. The only way that it would not do that is if these terms down here are getting infinitely close to 0. So something close to 0 plus about 0 plus about 0. All right, so as long as these values are getting infinitely close to 0, then it could converge. It isn't guaranteed to. But if we don't have it, if it goes to anything other than 0, then it diverges. That's it for today's notes. I will see you guys soon.